Errors that happen during replication and how are these errors corrected? A human cell can actually copy its old DNA in a few hours with a rate of error that's 1 per 1 billion nucleotide pair. So that's like an amazing job for our human cell. So we're talking about a very, very small amount of error. But what are these types of error that we're talking about? We have two types, mispairing and strand slippage. Mispairings from the word itself, so I'm putting a nucleotide instead of another nucleotide that's not complementing it. So instead of a T with an A, I put T with a G. And that's, of course, a big error. A strand slippage is basically when I don't have this fixed relief of stress. Remember this relieving of stress and the single strand binding proteins and all the topoisomerase 2 work that I need to keep it like from all the stress of the double helix. This stress can cause my double helix to actually squeeze a bit or give more space, which can cause to adding or omitting a nucleotide. So if I push more or push less, this can cause to looping out, okay, which means basically adding a new nucleotide, okay, or basically failing to put a nucleotide, which means that I'm omitting a nucleotide by failing to incorporate one of the nucleotides. Our two heroes that will go to check for mistakes and proofread the DNA are called DNA polymerase 1 and DNA polymerase 2. Basically, we'll focus about DNA polymerase 1. DNA polymerase 2 had another job, if you do remember, which was to remove the primers that were built by the primase enzyme on the lagging strands. But it also has a part job here in proofreading. But the main proofreader is polymerase 2. It can basically cut all the incorrect bases, okay, that are on the new DNA strand. And of course, building a new one. And for the building, he needs the parent strand as a template. These two together, they are good in correcting 99% of the mismatch that can happen, which is a very good amount of mismatch repair and repairing mechanism. This 1% that will remain unrepaired is going to eventually become a permanent change in my DNA, and this one we call mutation. Is DNA replication in prokaryotes the same as in eukaryotes? More or less, yes, with some differences. So they both share the same thing. They both share that they have an origin of replication. So I need to have an origin of replication. They're both double-stranded, so they both have unwinding of the double helix, a bubble, and a fork, and all these. Elongation happens always in the 5-3 direction. That's a must. And we always have a continuous senses of leading strand and a discontinuous of the lagging strand because of this having only 1,3' on one strand. So the other strand has to go discontinuously being built. And they all use primers for the Okazaki fragment synthesis on the lagging strands because I have a discontinuous strand as well. And they all use the DNA polymerase enzymes of 1 and 2 and 3, like builders and proofreaders and the one that removes the primers as well. So these are the things that they actually share together. What are the differences? We have 3 important differences. Number 1, it goes without saying, I have a small circular DNA molecule in prokaryotes and a long linear DNA molecules in eukaryotes. This means that the rate of replication is way faster in prokaryotic cell than in eukaryotic cell. And to speed up things, okay, I will need one origin of replication in my circular DNA molecule because it's circular. So if I start here at one point, eventually I need to end at the same point. But on the long linear DNA molecule in eukaryotes, I may have thousands origins of replication. And I need to, as I said, to complete this replication in a couple of hours. So I need a lot of origins of replication when I have a long linear molecule of DNA rather than one origin of replication only on the circular DNA molecule of prokaryotes. The last difference is that the DNA polymerase enzymes are a bit different. So they detected 5 in prokaryotes while 13 in eukaryotes. And that's our final difference here. Final part that we come to is a problem. The DNA molecules in eukaryotics are linear. That will create a problem, because when the final RNA primer from the 5' end of the lagging strand is removed, and I do not put any adjacent fragment onto it, no nucleotides added, on this, there's always going to be a gap, which means that on this linear DNA molecule, I'll start by time. Every replication round, I will lose some important genetic info, which can contain coding information, right? And of course, this will lead to shortening of my DNA molecule. That problem doesn't happen in a prokaryotic cell because it's a circular molecule. So it's protected by its own circular shape. But here in eukaryotes, it's linear. So God created us enzymes called telomerase enzyme. Thus, this telomerase enzyme, it has the ability to build a repeated sequence of nucleotide that we call telomeres. It's a very highly packed, repetitive sequence, this telomeres. And these telomeres is basically there to keep the lagging strand from losing any important genetic material. But scientists found a very important thing connecting these telomerase activity enzyme with aging. They found that the telomerase enzyme is highly active during childhood, but it slows down by getting older. And the older a person gets, the less activity is recorded from this telomerase enzyme, which means more genetic material, less repetitive ends, which means that I can lose some of the genetic material. And of course, there is a lot of research paper connecting these telomerase activity and enzyme activity to aging.